Welcome to Apply Day 2020. My name is Alex Sinclair. I'm in a simulation here at Applied Engineering. A little bit about Applied. We really have two parts of our business. We are a design and manufacturing consulting engineering firm, and we also have a software development side. And so we are standing by, ready to help any customers in the region here with any of their design or manufacturing engineering needs, as well as software development. And so with that being said, I think we can get started with this Applied Day webinar titled FEA Overview and Best Practices. So jumping right in here, the topics we're going to cover in today's webinar, we'll start out with just kind of the general information about finite element analysis. Really, this is geared towards new analysts and engineers. But don't worry if you do have some experience in FEA or do have some exposure, maybe here and there. This will still be a very good webinar for you. There'll be a lot of good information, and really what we're going to try and do is incorporate a lot of the things that we commonly do here at Applied in our simulations. We're trying to kind of convey that to everyone. We will cover the FEA fundamentals from a mathematical point of view, and I think that's very important to kind of understand, what the software is doing and how it's kind of influencing the mathematical model in the background. We will also cover the steps of the FEA process in detail, and so there are many steps. We'll kind of get through that. Again, we'll cover the best practices that we try and cover and do here at Applied to create computationally robust models, and we will kind of end on some of the challenges that kind of prevent us from setting up some of these simulations in the most realistic way possible. So let's jump right in. We'll start off with a question. What is FEA? Okay, and FEA, it stands for finite element analysis, and it is a numerical analysis tool that we can use to solve engineering and mathematical problems. Okay, and so really what I think is important to understand here is that what the FEA software does is it takes our CAD geometry, it takes whatever kind of products that we want to learn more about, and it basically turns that geometry into a mathematical model that the computer can solve, right? And so in FEA, we're typically applying some kind of loads, or there's several applications. This one is specifically centered on static structural FEA, where we're applying loads and specifying boundary conditions and looking at the responsive structure. But we're not only limited to that, we also have dynamic FEA, things like impact and vibration can be studied, thermodynamics, fluid flow, things like electromagnetics. And so there are many common applications, but again, we're going to focus here on static structural FEA. And so we kind of defined FEA as the numerical tool, finite element analysis, but that really begs a question of what a finite element is, okay? And I think the easiest way to explain what a finite element is with the picture of these wrenches here. A finite element is just a block, okay? And we use many of those blocks to basically approximate some type of given geometry. And we call those blocks finite elements. And so from here on out, we'll refer to them as finite elements. And we use a finite number of them to approximate a geometry. And you can see with these wrenches here, the more of those elements that we use, the better that approximation becomes, right? And so there's kind of a trade-off between the more elements we use, the better our approximation becomes, but also it becomes more computationally expensive. We need more powerful computers, or we need more time to solve these problems, okay? Just a little bit about FEA in general here. Again, it's an engineering tool. And what we really want to do with this tool is we want to use it to better understand our products, and we want to use the tool to be able to generate some data about those products, and we want to use that data to make some type of downstream decision, okay? And again, I mentioned this kind of in the finite element portion on the previous slide, but FEA is an approximation. There is approximation built into every single step of the FEA process. And I think that's important to understand, that we're not dealing with an exact solution here. But FEA can be very accurate. And if we are confident in the results and the data, we can use that data to make some important decisions to hopefully save us time and money in the products that we're producing, okay? Now, with that being said, I think it is very important to highlight right up front here that FEA is not a substitute for proper field testing. It's not a substitute for good judgment, right? We don't want to run these products and these designs through our finite element software and get results that we aren't confident in, and use that data to make decisions, right? If our product has some type of safety issues with it, we always want to make sure that we're putting our products through proper field testing to be absolutely sure. But FEA, it can be very useful and very valuable given the right circumstances. And so one of those circumstances is when we can kind of plug it into the design cycle. And I kind of define the design cycle as the design, build, test cycle of our products, right? So we start out with our detailed design phase. We might have a few different iterations there, and we move into actually building some prototypes and testing those prototypes. And so this cycle can be very time consuming and financially expensive, especially if we have to go through the cycle multiple times, right? And so really, if we can plug analysis in here and we can go from design to analysis, back to design, back to analysis, if we can do that a few times and save us the time and effort of building multiple prototypes and testing those prototypes, we can get a lot of value out of FEA. We can also, a lot of the projects we do for our customers will be on existing designs, so we'll just go through and we'll analyze those designs just so our customers can better understand their existing designs. So our value of FEA is not only limited to plugging it into this design cycle, but that is one area that we do see a lot of customers really benefiting. The next slide, we've got an example of really some poorly done FEA, and that's in the Sleep Array offshore oil platform, and this oil platform sunk in 1991. I don't believe there were any casualties associated with the sinking of the platform, but it was a total economic loss. That oil platform went all the way down to the bottom of the ocean. And in the subsequent study of, why did this oil platform fail, they did trace the failure back to an error in the finite element approximation of what was called a tricell. And so the little GIF image on the bottom, there's the oil platform, and it's held up by the ballast tanks. And the tricell is what stabilized and held together those ballast tanks. And they found that the finite element analysis performed on that tricell underpredicted the shear stresses by 47%, which is what led to the failure of the tricell and thus the sinking of the platform. And so with that being said, I think that it's important to be confident in our FEA data that we're generating and the results. And in order to do that, I think that it's equally important to have a strong fundamental understanding of the finite element method and FEA software. And that kind of goes hand in hand with a strong foundation in basic mechanics principles, right? We want to be able to do some classical validation of these FEA models, and we want to have good intuition as to what the results should kind of look like and things like that, so that we can be confident in the results and we don't run into issues, downstream by making poor decisions based on poor data. Okay. So moving on, we're going to look at the FEA fundamentals and kind of the mathematical model that's really what's going on in the background of the FEA software, okay? And I think it's important to understand the basics of this mathematical model, just because when we're clicking around in the FEA software, this will kind of give us an understanding of what we're doing in the FEA software and how that's affecting what's going on in this mathematical model. And we're really going to focus here on linear FEA. And so we all know finite element analysis can be nonlinear, but we're going to focus on linear here just for simplicity. And so moving into the equation here, we see F equals KD, and so that F is a vector, the K is a matrix, and the D is the vector. And this, a lot of you will probably recognize that this is very similar to our spring equation, right? Our stiffness of a spring, okay? So we'll kind of go through the equation a little bit. The F vector is the vector of element nodal forces, okay? And so this is all of our applied forces, and this is all the internal forces at all the nodes in those elements that we've used to create our model, right? So all of our applied forces and our internal forces at all the nodes, that's what makes up the F vector. Okay, moving on to the K matrix. This is called the element stiffness matrix. This is made up of our mesh. Okay, so when we generate that mesh, that is coupled with our material properties, and those two things come together to build this element stiffness matrix. The D is our vector of element degrees of freedom. Okay, and so these are basically all the displacements at all the nodes, okay? And some of those we know, some we don't. That's similar to the element nodal force vector. Some of those forces we know, some we don't, okay? And so there's unknowns in the F vector and the D vector. The K vector is all known, okay? And so when we actually go and hit the solve button, we're going to solve for all the unknown Fs and all the unknown Ds, okay? And what's really important, and kind of what we'll get into, is all the unknown displacements, okay? We want to know the displacements at every node in the model. And so when we actually generate the system of equations, we can have many, many equations. A lot of the simulations that I typically work on can have anywhere from tens of thousands to millions of equations that the computer is solving and generating. Okay, so once we have that D vector, once we have those displacements, okay, and we're focusing again on linear FEA, and we're further focusing on the use of metallic material models, okay? And so when we have that D vector, those displacements, we can plug those displacements into our constitutive equations, okay? And this is called post-processing. This is where we've actually already hit solve, we have our results, now we're going to post-process that data into something that we can actually use to make decisions based on. And so our constitutive equations are going to relate our displacements to our strains, okay? So blue circled there, those are all our displacements, and those are the relations that allow us to calculate our normal and our shear strains. Once we have our normal and shear strains, again, if we're working with neo-Hookean linear metals, we can use those strains to calculate our stresses, okay? And our stresses, in a lot of cases, are really what we're interested in, right? I did mention that we are focusing on specifically linear FEA. I do think it's important to point out some of the ways that our model can become nonlinear. First and foremost being our geometric nonlinearities. And so these are going to happen when we have large deflections or rotations present in our model. A good example of that would be like a fishing rod. When you've got a fish on a fishing rod, that rod can basically double over, it can deform quite a bit. And so if we were going to simulate something like a fishing rod in finite element software, what would happen there is that our K matrix, right, that K stiffness matrix would actually become a function of the displacement, okay? And so that would turn the simulation to be nonlinear. We also have element nonlinearities, and I primarily define these as contact nonlinearities. So if we have complicated models that have different types of contact, like frictionless or frictional contact that we want to simulate and capture, there's going to be a nonlinear solution process associated with that. And maybe the nonlinearity that we most can kind of most easily associate with would be our material nonlinearity. So if we're dealing with plasticity in metals, or maybe different plastic materials or hyperelastic materials, we will have nonlinear material models, and again, our K matrix will become nonlinear. And all of these lead to the need for an iterative solution process. So if we have a nonlinear FEA model, we need to use an iterative solution process to solve it. We can no longer directly solve for the single unknown variable. We have to use the iterative solution process, which is basically a guess and check solution, okay? And so there's quite a bit more associated with doing that, and it can, from time to time, involve quite a bit of troubleshooting. If some of your things aren't quite working out how you thought they would, you might need to do some troubleshooting on your model. Next slide we have here, and I think this is equally important, is to look at defining our analysis. I think this is very important because we need to have some type of goals and expectations, and really almost kind of a roadmap for what we want to do, how we want to do it, and when we get there, what are we going to do with that data, right? Simulation can be pretty resource intensive, and so we don't want to be carrying out this analysis if we don't really have clear goals, and if we don't have an idea of what to do with the results. So determining a strategy for carrying out that analysis, as well as validating and verifying those results, is very important again. And so really what we start with when we start looking at how we're going to carry that analysis is what assumptions and simplifications can we make, and how is that going to lead into actually setting up our model and carrying out the analysis. I think moving on, we're going to look at the analysis workflow. So this is going to be all the detailed steps of the analysis. We'll go through each one in detail, and this is where I'll try and point out some of the best practices or common techniques that the simulation engineers here at Applied try and use. So jumping right in, we start with our geometry step. And the geometry step really is typically the most time-intensive step. And so this is where we're taking our CAD geometry, we're importing it into our FEA environment, and we're starting to set it up. You know, what parts are we going to remove? How are we going to connect everything together? How complicated is geometry? You know, all those types of things are all kind of taken care of in this step. One thing I do want to point out is that the geometry step kind of does go hand in hand with our connection step. We do need to be thinking about how we're going to set up a lot of these connections. Some of them are kind of done in the geometry step, and we'll get into that. And some of them are also kind of done in the connection step, where we're actually defining different contacts and degrees of freedom and things like that. After we've kind of got our geometry handled, we move into selecting our elements. Element selection is kind of an advanced topic. Once we select those elements, we'll actually we'll build all those elements up into our discretized geometry. So we'll take all those elements and we'll apply them over our geometry and build a mesh. This is called meshing commonly. Once we're done meshing, again, we'll get into the connections phase where we're going in and again designing and defining rather those contacts. Loads and boundary conditions would be next. And this can be, and we'll talk about this can be a challenging step, but we really need to focus on real world loading and real world boundary conditions. Then we're gonna hit the solve button. Okay, then we hit the solve button, we get our displacements and our unknown forces, and then we can go ahead and post-process, get our stresses, strains, displacements, things like that. So diving right in to the first step, the geometry process. Which parts do we need? What do we want to exactly do with the geometry? Can we remove non-structural components? The answer is, if the components don't really contribute to the overall stiffness of your geometry, then absolutely we need to remove them. We don't want those in there. Typically, we'll remove a lot of the insignificant features, small holes, small rounds, things like that. Those small features take, you know, quite a few elements to capture those, and if we aren't really concerned about the area that the small features are present in, we can remove those, and we can always add them back in later if, you know, something comes up that we do want to look at those. So typically remove those. Symmetry, this is kind of a big one. We can really decrease the complexity of our models if we can take advantage of some type of symmetry, whether it be some type of planar symmetry or axisymmetric models. We really want to stress that that's important to look at those symmetries. Topology sharing is a big topic here, and we'll kind of go through this on the connection slide. But what topology sharing is where we are actually combining multiple parts into one single part, okay? And this can be a very powerful tool to simplify our models, especially for thin sheet metal components that are welded together. Topology sharing can be very advantageous, and we'll go through that a little bit more in the connection slide. Moving on to elements and meshing. Again, this is an advanced topic. Element selection, the type, the order of the elements. You can really dig into that quite a bit if you'd like to. But we won't cover it too much here. What I do want to highlight is the primary types of elements: continuum, solid elements, shell elements, and beam elements. Those are the types of elements that we typically find ourselves using here in the applied simulation team. And what I really want to do with this slide is highlight the difference between solid and shell elements, okay? So solid elements really contain the greatest amount of detail and accuracy. They're a great element to use, very common element to use, and we'd like using them if we can. Some of the negatives of the solid elements, there are a few. First and foremost, they're very computationally expensive, okay? Usually if we're using solid elements, we're going to need a lot of them in order to mesh our models. And so they do take quite a bit of computational expense. And really part of that is because we have to have some thickness considerations. Low order solid elements, we do want to make sure that we have multiple layers of those solid elements through the thickness of our parts. And the reason behind that is if we don't, then we have trouble accurately capturing the bending. And so when you combine needing, you know, multiple layers of these solid elements through our parts, and the fact that they're computationally expensive, we find that if we're using a lot of these solid elements, It takes a long time to solve our models. And so that's kind of where shell elements come in. Shell elements are very computationally inexpensive. They're a 2D element. And so really what they do is they take the thickness of that part and they incorporate it mathematically into the model instead of actually stacking those elements together to get the thickness of your part. We're just going to incorporate the thickness mathematically. They're very computationally, again, inexpensive. And they're very accurate. We like them a lot. We use them all the time here at Applied, especially when we're working with weldments, thin sheet metal weldments. Shell elements work very well. One challenge with shell elements is that there's really no rule of thumb for when to use them. We really want to be using the shell elements when the thickness of the part is fairly minimal compared to the other dimensions of the component. So, excuse me, getting some background noise. Again, back to the shell elements, we want the aspect ratio, the thickness of the part to be very low compared to the overall length and width or the other dimensions of the part, okay? If those things are true, we really want to try and use those shell elements. Okay, so once we select those elements, we get into assembling those elements into a mesh. Okay, and the sizing of those elements is very important, and we'll discuss that a little bit on this slide. The sizing of those elements can greatly influence the results. We really want to have good fidelity with our analysis, and so we want to make sure we are capturing the results that we're looking for, but we need to balance that with computational expense, right? And so the two graphs on the bottom here represent the von Mises stress and the displacement magnitude in a flat plate that's constrained on all four sides and loaded in the middle. So again, we have a flat plate, it's square. We are constraining it on all four sides and loading it in the middle. And what these graphs are showing us is the result of the displacement magnitude and the von Mises stress versus how many elements we are using to approximate that geometry. And so we can see that if we're using a very low amount of elements, we get some very erroneous data, right? And when we increase that element count, we start to converge on what we would say is the correct result, okay? And so a lot of this comes from just gaining experience and carrying out a lot of simulations, and that'll help you kind of gauge, you know, how big your meshes should be. But if you're not sure, you need to do what's called a mesh convergence study, which is exactly what we've done here. We need to actually go in and solve the model multiple times with multiple different mesh sizing to make sure that we are converging on our, you know, correct result. Another thing I'd like to kind of comment on mesh sizing is our D-feature size. And this is something that's kind of been bugging me a little bit lately in some of the simulations I've been working on. D-featuring is something that happens when you go and mesh your geometry. Your mesher will automatically defeature anything underneath your defeature size. So this can be a very powerful tool if you don't want to go and manually defeature your geometry. Your mesh, you know, if features are underneath that defeature size, your mesh will just remove them, okay? And occasionally, you know, that can be a very valuable feature and a time-saving feature. But sometimes you have small features that you do want, okay, and you didn't remove when you were working in the geometry phase, only to find out that the mesher removed them for you, okay? And this has happened to me a couple times. After I've been reviewing the analysis results, you go back and you see that, okay, it looks like some of these small features that I was interested in have actually been defeatured. So something to watch out for. A little bit about the mesh types and quality. This is another advanced topic. We won't dig into it too much here, but there are many different mesh types, and we do want to keep an eye on element quality, especially if we have large deformation present in our models. And so if that is something that's you're interested in, you can perhaps reach out to me later. We can talk a little bit about it. There's a lot of good information online on this topic as well. Moving on to connections. Okay, this is a very important step in the FEA process. The connections are, again, they're an advanced topic, and we'll try and go through some of the basic connections here, kind of from a high level overview, just so we understand how to set some of these things up. And so we had talked a little bit about shared topology on the geometry slide. And again, that's where we're merging multiple bodies together into one body. Okay, and I've got an image here. These are a couple of shelled sheet metal bodies. Okay, and in the left bottom image, we are not sharing topology, and so we are not node sharing. And so you can see on those meshes that the nodes at the bottom of the vertical plate are not being shared with the nodes on the horizontal plate. Okay, those are two individual bodies. So if we were to run the simulation in this way, we would need to define a connection there. In the upper right image, we are sharing topology, and so you can see that the nodes between the two bodies at the connection point are actually sharing. Again, shared topology can be a very powerful way to transfer load from one part to the other, and we can retain some individuality, some individuality between the parts. For example, the parts can still have their own different thicknesses, and they can still have their own different material properties. So we can still maintain some of those types of things. And topology sharing is very computationally inexpensive. It is the easiest and most robust way to transfer load from one part to the other. Okay. Let's talk a little bit about the connections in general now, and we'll kind of start with bonded connections here. Bonded connections can be linear, and they're generally very stable. They're usually the default type of connection. If you default in your geometry and it builds connections for you, it's going to default to the bonded connection. You always want to be building your own connections so you understand the load transfer through the part. I think that's very important. And we will get into a little bit here kind of how connections work in general, and this will apply to many different types of connections, not just bonded. So when we're setting up these connections, we're always going to start by defining our contact and our targets, okay? And these are going to be explicitly, these will be our contact nodes and our target nodes. So those will be defined, maybe it's a face, maybe it's an edge, maybe it's vertex, individual nodes. We're going to define those. And then the software is going to go ahead, and in the case of bonded contact, it's going to glue those nodes that you selected together, okay? And it's going to do that by looking at the pinball radius of the contact, okay? And so the pinball radius is basically a sphere that's placed on the contact nodes, and it will look for any target nodes within that sphere, and it will bond them together. And so the pinball radius is a very powerful tool for fine-tuning our connections, okay? A lot of times the pinball radius can be automatically set by the software, but as far as I'm aware, most finite element softwares will give you the option to specify pinball radius. And so we can use that as a tool to either make our connections a little more fuzzy, or maybe we can tighten them up and make sure that the load is transferring only through, a very specific set of nodes. And we kind of have a picture here. Those purple lines with the arrows pointing to them, that would be an example of, some nodes that are kind of a little bit farther away that we're able to spread the load out to. Maybe this would kind of simulate almost like a weld bead, for example. Some other types of connections, generally the other types of connections besides bonded contact are generally non-linear, which means they're less stable, and we're going to need that iterative solution process. And some of them are a little bit more advanced, especially when we get into troubleshooting and getting them to actually work how we want them to work. They can be a little bit more time consuming. Some examples of these other types of contact are frictional and frictionless contact. And you can kind of see the contact in the upper right picture there. We've got a pin that's in contact with the inner race of that ring. And so that would be a very realistic way to set up the contact stress there. We would actually use a frictional contact. If we were to use bonded contact there, our Hertzian contact stress in that situation wouldn't be anywhere close to correct. But if we want to calculate the contact stress using a frictional contact, we can get very, very close to the analytical answer there. And so that's a great example of kind of the difference between those types of contacts. We also have joints. Joints are degree of freedom constraints, and so that's where we're actually going to constrain the degrees of freedom of different bodies and different parts relative to one another or relative to ground. And we have a kind of an example here of a hinge joint there. So we're allowing the nodes internally in that hinge to revolve around one another. Joints commonly used for things like pins, bushings, bearings, cylinders. Joints are very robust way of setting up your connections. They're generally very stable. They don't require a lot of troubleshooting if they're set up properly. One drawback to the joints is that it is possible for the stress state around the joint to be a little bit off just because the nature of how the joint works. And so typically what we'll do here at Applied when we're working on a project is we'll set up joints in areas that, you know, we may not be as concerned about the stress state in that area, and we'll use more realistic contact like frictional and frictionless contact if we are very concerned about a specific joint. So moving on to boundary conditions, I'd mentioned, you know, this is a very challenging topic. And really what the challenge is accurately representing the applied loads and the boundary conditions. You know, how can we take something in the real world, get it into our computer and simulate it, you know, as accurately as we can, and really capture what's happening to that geometry in the real world. It's really easy to over-constrain our models, and over-constraint can really lead to erroneous data. A good example of over constraints is just using fixed constraints. You know, we can just fix one part of our model. Very easy to do that. They provide very stable solutions, but really fixed constraints are not realistic. There's nothing that's infinitely stiff, right? And that's what you get with a fixed constraint. So they are rarely the right choice, but occasionally they can be a good place to start. It can help you get your model built and solved, and so you can kind of see if there's any other issues in the model. I do have a good example here of some poor boundary conditions. This is a ramp. This is a hinged ramp. It folds on the hinge point there in the middle. We have boundary conditions set up at A and B, and we have load applied at C, D, E, and F. Okay, and so this ramp, you would use this ramp to drive like an ATV up into the back of a truck. Okay. So again, constrained at the ends, loaded in the middle. And when we use fixed boundary conditions at A and B, this is what the stress state of that hinge looks like, okay? We can see the key there. It's very low stress. That's in PSI, so we're seeing very low stress. Not a lot of concerns here. So this result would lead us to believe that our design is adequate and that we can move forward with, you know, building and testing this ramp. Now, if we use a little bit more realistic boundary condition, we see the stress state on the right. We have very high stress in that hinge. And when this ramp was tested, the first time an ATV was driven up into the bed of a truck, all the welds on the hinges, all the welds cracked. And the second time the ATV was driven up the ramp became two pieces instead of one. It broke in half right on the hinge, right along the weld lines there. And so this is a great example of how poor boundary conditions led to a lot of wasted time and effort on building this ramp. I do have a slide here on failure criterion. I think this is probably a topic, a subject that a lot of you are already familiar with, but I think it's important to kind of highlight. This is basically, you know, some of the stress results that we're going to be post-processing out. How are we looking at those? A lot of times we'll look at the distortion energy theory. It's typically pretty good at predicting failure for ductile materials. One of the drawbacks of the distortion energy theory is that it doesn't really differentiate between tensile and compressive stresses. The distortion energy theory, it's also known as von Mises stress, by the way. And really what it does is it takes our principal stresses along with our maximum shear stress, and it turns all those into one scalar value to indicate the overall stress state of the material. And so we're kind of taking all the different stress types, lumping them into one thing there. And it is a great tool, but I do think it's important to look at the tensile stresses and the compressive strength, the compressive stresses in the model and kind of understand where those are. And we do that with our principal stresses. The principal stresses are, you know, they're more of a preferred predictor for brittle failure. And our principal stress is also what we're going to look at if we are doing any strain gauging. Okay, if we are doing any testing with strain gauging, we'll want to correlate that data with our principal stress state. And so typically here at Applied, we will look at both of these stress states, the distortion, the von Mises, and our different principal stresses to get an overall idea of the stress state of our geometry. Okay. Now, why are we even using FEA in the first place? Why do we want to use FEA over, let's say, our classical and analytical stress analysis techniques that we learned back in college, right? Those are very powerful analysis techniques, and I would highly recommend using those whenever possible. If your geometry is fairly simple, you know, we want to take a look at those analytical techniques first, right? And we can use those, if we do go into doing some FEA, we can use the results from some of those classical calculations to help validate our FEA. That's very important. But where FEA really has an advantage over our analytical and classical analysis techniques is that we can simulate complicated structures, weldments, and load paths. FEA takes the stiffness of our model into account, right? So in our classical techniques, we're not taking into account any deformation or any stiffness changes, okay? One thing I think that's kind of important to highlight here on this slide is that load is going to follow the stiffest path, right? It's got to go in somewhere and it's got to come out somewhere. And so it goes in where we apply the load to our FEA model, and it comes out where we apply the boundary conditions. It's going to flow from the inlet to the outlet, okay? And that's very important to understand, and it kind of even highlights how important our boundary conditions is, because they really influence how the load flows through the geometry, okay? And it's kind of like a water flow analogy almost. And we can use that to capture our stress concentrations, which is something that's a little bit more difficult to do with our classical techniques. Again, some of the challenges, we've been talking about those boundary conditions the whole presentation. They can be tough to come up with the right ones. And that's, you know, some of that comes from experience. Maybe you have some field test data that you can use to help you with that. And really, if we are going through and carrying out our analysis, you know, how do we define some type of pass fail? What do we do with that data? A lot of times what we'll do here at Applied is we'll actually do a comparative analysis. If we have some type of geometry that's been, you know, field tested and in the field for 10, 20 years, and we know it's good, we trust it, and now all of a sudden we have a new design, right? We have some type of new design, it's got some type of updates and design changes. We can actually run the analysis on both designs and do some comparison and say, okay, the new design, you know, it's better than the previous design, or at least it's not worse than the previous design. So we can use that to say, okay, we're very confident, you know, in these results comparatively, that we can move forward with the design change, okay? I do have a project showcase here from our friends over at Shoremaster. Shoremaster is a boat lift and boat dock company. They build all the fun stuff that you would want at the lake. And we recently finished up a project with them, an 8,000 pound hydraulic boat lift. And some of the kind of design details of this, the retracted height of the boat lift was to be 21 inches, which was 5 inches lower than their current product. And we were looking for a cost reduction of around 10%. And so we used finite element analysis quite a bit to supplement in the design of this lift to make sure we were meeting all of our structural kind of targets comparatively to the old model. And I do have the finite element model to show you actually. And so what's kind of cool about this lift model, this is a side view of that model. What's kind of cool in this little animation is you can see when you apply the load to the model, you can see the structure. You can see the structure basically respond to the loading, and then once the response is done, we'll actually send the hydraulics through their range of motion. So we'll allow the structure to respond to the load, and then we'll actually actuate the hydraulics through the range of motion to make sure we're kind of capturing the stress states of the lift through its entire range of motion. And so I'll play it a couple times for us here. Hopefully everyone can see it's starting to respond to the load, and then the hydraulics kick in. So again, play it one more time. So this particular simulation had 6 or 7 different weldments that we had to build in the finite element modeling environments. And then we have several joints, several connections. There's quite a bit of frictionless contact that we use in this, and quite a few joints to define all the degrees of freedom throughout the model. And so a fairly complicated model of basically the whole machine that is the lift. And so a big thank you to our friends over at Shoremaster for allowing us to work on that project with them. It was a lot of fun. I've got a literature slide here. This is mostly just geared if you are starting an analysis program. ISO 9001 would be the formal guidelines for an analysis program, and VV10 there, that'd be the guide for verification and validation of computational solid mechanics. Mostly, I believe that document kind of looks at the mathematics behind the software. So just kind of to be aware of the standard documentation. A little bit about applied engineering. We are 100% employee owned. We like to think that we have some good engineers on staff here, some talented engineers on staff. We are pretty flexible with our customers. We like to be adaptable and help you out wherever you are, however you need us, basically. And again, I did mention at the beginning that we work in the engineering and manufacturing design space, but also we do have an IT group as well. Some of the things that we've been able to do for our previous customers, specifically as a result of simulation projects that we've done, they're kind of listed out here. We've reduced prototype costs, accelerate design cycles, decreased defect rates, remove product costs from over-designed components and systems, improve safety, and gain general insight and product performance, structural behavior that otherwise our customers didn't know before. We do have the best tools in the business for carrying out finite element analysis here at Applied, and so that's a big advantage for us. And with that being said, I'd like to thank everyone for coming out to Applied Day today and listening to this webinar. This is my contact information. If anybody wants to get a hold of me, ask any questions following the presentation here. We will have some time for questions at the end, but feel free to reach out. I'd love to hear from you. This is our general sales email and number. We do have some other upcoming webinars. We do a lot of webinars here at Applied on some of the Autodesk software. And so those webinars are great if you need to learn, what's new in those or kind of the basics on how those work. And with that being said, I'd like to open it up for questions. Looks like we have a question here. What software do you prefer to use? We typically use ANSYS here at Applied. In my opinion, that's kind of our enterprise, our top level enterprise software. It's fully featured. It's not limited in really any way that sometimes some of our built-in tools can be. So we have several engineers in our Applied office here that are very experienced with ANSYS. All right, guys. Well, I'd like again to thank everybody for coming to Applied Day. It was great to host you all. And with that being said, have a great rest of your Thursday and enjoy the weekend.